Thank you very much, Chris, for this, and thank you very much for inviting me to be here today and talk at your conference. So I'm Grete Straume. I'm a mission scientist at ESA for the Aeolus mission. I've been working on the mission since 2004, so you're absolutely right. It's been long in the coming, but it's been very rewarding, and we're very happy to see the results that we have now 2 years after the mission launch. It's the first Doppler wind Lidar in space, and this has been part of the reason why it's been a challenging mission, really new technology in space and a real technology demonstrator. I'm doing this presentation, of course, also on behalf of a large team, Tommaso Parinello, working at ESA ESRIN, who's the mission manager, and the teams both at my premises in ESTEC in the Netherlands, our flight operations people in Darmstadt, and of course the science teams all across Europe and across the world, and of course also industry who's been building this mission. So next slide, please. So Josef already showed this slide. It shows where the Aeolus mission is located in our Earth observation satellite program. It's an Earth explorer, and as I mentioned, it's a demonstrator of new technology in space. And in this particular case, it's measuring winds, which is of use for weather forecasts. And if it is successful, it's a potential candidate for operational meteorological missions, which would be the family that you can see here on the right of this slide, which shows the meteorological missions we do together with EUMETSAT. So the scientific objectives of the mission is really to improve quality of weather forecast foremost, so have a positive impact and give you improvements by measuring winds globally from the surface up to 30 kilometers altitude. And these measurements will not only help us improve the weather forecast, but also our understanding of atmospheric dynamics in general. And this is also very interesting and important for understanding climate processes and also to improve climate modeling. The Explorer objective is to demonstrate space-based Doppler wind lidars in space and their potential for operational use for weather forecasting, as I was mentioning before. And we do that by measuring winds from the ground up to 30 kilometers. And we measure the winds actually along the laser beam, so along our line of sight, and we horizontally project these to the horizontal in order to measure mainly the east-west directions of the winds. We also have spin-off products, and these are atmospheric extinction and backscatter coefficient profiles. So these tell you where the aerosol layers and cloud layers are in the atmosphere. And this is very interesting also for air quality forecasting, to be able to detect aerosol layers coming either from anthropogenic activities or natural ones such as Saharan desert dust, or also, for instance, smoke particles coming off forest fires. So we have one payload on board, Aladin, the atmospheric laser Doppler instrument. So that's quite unique to have this one instrument specific mission. So here are some examples of the scientific benefits that we see from Aeolus now. You already saw this picture here on the right in the presentation by Josef. And what it shows is what the data does to the ECNWF model, so the European Center for Medium Range Forecast model. And what it does is to change the wind fields foremost in the tropics. Here you can see red colors around the intertropical convergence zone and the Asian monsoon location, but also in the convergence zones of the South Atlantic and the Pacific. So the figure shows you how much the Aeolus observation are actually changing the initial field of the forecast. And these changes, they can be good or bad, but we will see in some plots later that these changes are actually going in the right direction, pulling the model closer to, for instance, radio zone observations that we have in these areas. So several weather centers in Europe, in the US, Canada, and also in India have started to work with the data, and they see significant positive forecast impact of Aeolus when they assimilate it into their forecast models. So Aeolus is shown, as I explained in the figure, to provide important information in data-sparse areas, areas where there are very few wind observations available currently. And these are in the tropics, southern hemisphere, and in polar areas. And we see particularly a large impact in the upper troposphere, lower stratosphere, so between 10 and 30 kilometers in the atmosphere, where you also have very few observations. And as we speak, several forecast centers are actually assimilating the Aeolus winds in their daily forecast. ESNWF started already in January of this year, and the German Weather Service and Meteo France also started to use the observations in May and June this year. And the UK Met Office will start soon, this month actually. And the Indian Met Office is expecting to start in January of 2021. What's also exciting is that Aeolus is capturing vertically propagating waves in the atmosphere, and these propagating waves, they are triggered, for instance, by deep convective systems, also, of course, when the winds are moving over terrain on Earth, etc. And these waves are very much decisive for the weather development, and they're also impacting a lot the large-scale wind systems and their variability. And it's exciting to see that we can also see these signatures, and I will show some of that later. We've also seen recent changes in the stratospheric circulation in the tropics. This is called the quasi-biannual oscillation that is going on in the lower stratosphere of the tropical belt, and the Aeolus observation have been able to detect that there are changes to this circulation, which has started a couple of years ago. So the measurement concept, so we had the launch in 2018, mission lifetime is 3 years. The satellite flies at quite low altitude, 320 kilometers. And the satellite prime is the Airbus UK, and the instrument prime is Airbus France. So we have this direct detection, a Doppler wind Lidar operated in the UV, which was a challenge to get ready, because it's a very hazardous type of light frequency to operate in space in vacuum conditions. And it's emitting light at 60 millijoule at 50 hertz pulse repetition frequency, and we have 2 receiving channel, which allows us to detect winds both from molecular backscatter and also from particles such as aerosols and clouds. We measure 35 degrees off nadir, so looking to the side of the flight direction offline, and we measure the wind along the line of sight, and then we can project these wind measurements to the horizontal in order to get east-west direction measurements. And we also use the ground for calibration purposes. So as was mentioned before, it took a long time to develop the mission, and the main challenge was really the heart of the mission, which is the laser itself, the laser emitted. It's a very sophisticated optical instrument with more than 80 optical functions packed in a small box of a size of a shoebox. And another striking feature is also the telescope of the mission, which is 1.5 meter diameter, which is quite large for Earth observation missions, and is focusing the beam into an 80 micron field stop to get the measurements down to the instrument receivers. And that's been very challenging, and I will show something more about that. So what we measure is actually frequency shifts of the light on the order of 10 to the minus 15 meters. So that's actually of the size of a hydrogen atom. So that's the accuracy of the wind measurements that we need to make in order to achieve the wind accuracy in the atmosphere. So that's been very challenging, as we have seen, but we have managed to develop this. So the primary products are winds, and we have them available actually within 3 hours of sensing and delivering that to the MET centers with an accuracy of 3 to 7 meters per second. And we have quite low biases, which is less than a meter per second. And I also already mentioned our spin-off products on the right, on the bottom right. You can see an example of that. It's showing Sentinel 5P aerosol index measurements for a Saharan dust outbreak this summer. And Aeolus was overpassing this layer and was actually able to give you profile information to be able to locate the altitude of the dust layer. And this is very interesting for air forecast models that are currently actually running experiments to see how they can implement also Aeolus observations in their forecasts. We have had some challenges also, of course, of the satellite in flight. Overall, the satellite performs very well. All degradations and consumables are as expected, actually, and with lifetime. And we have also had quite a high number of special operations. The biggest challenge has been the flight lasers, and the first one was degrading with time, so we had to change to a second one last summer in 2019, and this one has shown to perform very well actually after some initial drop in the energy, which you can see here on the figure on the right in the purple. It's actually been stabilizing since early this year. And with some recent readjustments that we did this week, we've managed to get the laser output energy up to 68 millijoules, which is good news, with improved accuracies of our winds. The remaining challenge is that we have a slow decrease in the atmospheric return signal, which can be attributed to some slow drifts in the laser line of sight and also in our telescope management, which I will mention in a minute. And there are ongoing investigations with ESA and industry and external expert, which have set up a roadmap to mitigate this. And we're not expecting to fully recover our atmospheric signal, which is shown here in the red curve on the right, but in order to be able at least to regain quite some of it with the current ongoing instruments adjustments that we do. We had at the start of the mission wind biases that we saw in the measurements, and these were investigated and found to come actually from temperature variability on our large telescope. So the Aladin primary telescope is 1.5 meters of diameter, and it was known to be temperature sensitive during the design, and hence we have included, of course, active thermal control and in the mission design. We also have, in addition, the possibility to use ground returns, which have zero Doppler shifts, so you have zero wind from those. And those can be used to correct for any remaining biases coming from either mispointing from the satellite attitude or also from the effects on the telescope temperature. But the use of those were a bit hampered by the fact that we had less atmospheric return signal than expected and fewer valid ground returns. So the Aeolus DISC team, which are experts on different MET centers and science centers in Europe that work for us on the algorithms, they found the root cause of this coming from temperature variability on the telescope. So as we fly along the orbit, the top of the atmospheric radiances are varying with, for instance, cloud cover and also solar reflectance, and this gave us some biases in the winds, and this has now been effectively corrected for in the ground segment. So we're very happy about that, and these recent inclusions, which we included in April this year, made us come down to close to the bias requirements of the mission. Ground segment is working very well. We're having a near real-time delivery until almost 100%. So that's excellent news. And we also had our data release to the public users in May this year, which allows near real-time wind measurements. So here, some science results. We had a recent workshop this week where, for instance, the UK Met Office and also ESA showed very positive impact of the Aeolus winds on their measurements. It can be shown here, and on the left we have some scorecards with green numbers showing that Aeolus improved the winds on all attitudes for different parameters. And on the right-hand side, you can see ESA forecast at different forecast lengths from 12 to actually 7-day forecast on the right, and the blue colors and the hashed areas show where areas have positive impact, and that's particularly in the tropics, upper tropics, but also in polar areas for many days ahead. Also exciting to see at the workshop was that climate change is causing changes to the global circulation, and this leads to changes in the monsoon, this quasi-biennial oscillation I talked about before. And it's been seen also in Aeolus measurements that we can capture this disruption to the quasi-biennial observation with the Aeolus measurements. That's work done by Tim Banyard at the University of Bath and Professor Osprey at the University of Oxford, which are showing that Aeolus observations are contributing to solving this issue. And we've also seen Aeolus capturing gravity waves, and this is some work shown by a French group at La Réunion with ground-based lidars and radiosondes, and we can see that these gravity waves are also captured well by Aeolus. We also have upcoming campaigns to look more into atmospheric waves and how they drive atmospheric dynamics. This is just shown here, some campaigns from next year, and these are very exciting results that we look forward to. Going to the follow-on, NWP centers show positive impact. So there has been an interest by ESA member states and also by EUMETSAT Council to look at the possibility to launching an operational follow-on mission to follow on this data record in the operational MET program. And we are therefore having ongoing activities at ESA in order to mature the technology to make it fit for such an operational mission. So to come to the conclusions, here we're flying since 2 years. We see great significant impact on forecast and also in science. And we're happy to see even more centers coming in and using the data now. And we're looking forward to see what can be done for a potential follow-on mission. With this, thank you very much for your attention.
Okay, thank you very much, Anne Grete. It's really interesting to see this data finally, and it's quite gratifying to see that you're seeing the QBO signature. As somebody who was in the group in Oxford years ago and knowing the work that Leslie Gray and her team have been doing, it's great to actually see this in the data for them to have some more information to go with that. Just a quick question on the near real-time stuff. What is it that limits you to delivering in 3 hours? Is it the downlink time?
Yes, it's really the number of ground stations you have. So we have 2 ground stations basically now, and they're dumping the whole orbit, which is 90 minutes. Right. So we are dumping once per orbit, and then you need the processing time, which is quite quick actually, but it's more the number of ground stations you have. Okay. So the more ground stations, the more you can downlink, of course.
And we've got a question from Tony Sefton. He says, is the proposed Aeolus follow-on mission a direct repeat, or is with a modified payload, or does it have a different orbit, or are there any other changes, or is it just a repeat?
So they're looking at that now, and there are many possibilities. Of course, we're looking at to increasing the performance and to foremost mitigate the problems we had now. We had lower atmospheric signal than what we expected. So they're working on mitigating this to make sure we have the same atmospheric return as we expect, but also to, for instance, boost up the performance of the lasers. And also the orbit plays a role. We probably will stay with the same orbit orbit, which is dawn dusk, morning evening orbit, because that's shown to be also a good orbit for forecasters. But we're looking to have also better vertical resolution. That will be important for the follow-on.
So Stuart Turner from the Met Office has asked you a question as well. He said, can you tell us a little about how the technical challenges from Aeolus can be addressed to achieve a reliable follow-on mission? That's a bit of a leading question, isn't it?
Yes, indeed. So what we're looking at now is, of course, to make the laser technology robust, to be able to also have higher energies to come out of that. And the overall mission, also the loss we see in the atmospheric return path, which is caused a lot by the challenges in operating this large mirror and focusing the signal onto this small field stop to improve there. So these are the challenges that have been looked in particular. We're not going to go to different operation modes to do some scanning, etc. That is very complex to do, but really to provide better observations with better vertical resolution and to get better accuracy. That's the baseline of a follow-on mission, and make it robust for operational use. That's of course very important to
so the
allow
challenge with the mirrors. The challenge with the mirrors, is that the reflectivity changing, or is that
it's to make sure that that you don't have too large aberration, and also that you're not having a wandering of your focused beam.
Changing the aberrations and the quality of the image.
Quality of the mirror is important to look at improvements there, and also the thermal control of the telescope in order to make sure that you can focus. You can also think about going to bistatic, for instance. That's also one of the candidates that's being looked at.
So the challenge is that you've got this varying temperature around the orbit, which is causing the optics to distort effectively, and causes you a loss of image quality. Okay.
Yes, okay. The whole mirror actually. Yeah.
Yeah, fantastic. Yeah. Okay, well, thank you very much for your talk. It's been very interesting. I'm afraid we don't have any time for more questions.